Welcome to this Frequency Matters podcast series. I'm Pat Hindle, Media Director for Microwave Journal, and I am joined by another host, Sean Darcy, Senior Director of Aerospace and Defense at Infineon. And today we have a special guest, Andy Lowery, CEO at Epirus. Welcome, guys.
Thank you.
There's been a lot in the news and technology front about drones and other autonomous vehicles, so I thought this would be a great subject to tackle in this episode. Andy is an expert in this area, so glad he was able to join us today. So, Sean, why don't you kick off the discussion?
Sure, and thanks again, Andy, for joining us. Very curious to hear both about your thoughts and a little bit about what you guys do in your company. I find it pretty fascinating. So I guess I'll start off with a lot of the high power microwave, or what we call, directed energy systems. They've been around for probably a rather long while. But can you tell us what these systems are comprised of, what they do, how they work, and what their applications are? And where do they fall as far as the envelope of where you're protecting? If you look at your zones or concentric protection ring, kind of let us know where that fits.
Okay, yeah, that's a great question, because I think there's kind of a fair amount of confusion about the space and the history and how things are evolving. There's recently in the news, there's an award for something called Defend. And I think there's a subsequent award that the Navy advertises putting out a high-powered microwave system. But, when you talk high-powered microwave, a lot of times what you're referring to is a system that uses what us in kind of the RF land or the systems land call a backdoor technique versus a front door technique. And I think this is probably, in my mind, in the way I define it anyway, is a critical difference between high powered electronic warfare, so maybe HPEW, versus high powered microwave. And why I say that is that if you look at traditional jamming, like drawing back from when I was a chief engineer electronic warfare for Raytheon, when you look at traditional standoff jamming, it uses the receiver and the digital and all of that to get into the system and then do its little work and then come out with some analog effect that then, of course, disrupts or disables the system you're trying to go after. Well, the difference between high-powered microwave is that you have a system that doesn't go in through the receiver, that doesn't go through the antennas, that actually just goes straight into the wires and the connectors and the analog circuits. But then once inside the analog circuits, either can do something like damage them by overheating or creating too much energy for the thing to deal with, or by just confusing the electronics by, let's say, overloading a comparator circuit or doing something to an op amp or putting some energy where it shouldn't be, and then the self-protect circuits or just it confuses a servo or whatever, shuts the thing down. And that could be a drone, that could be consumer electronics of any kind. It could be the consumer electronics that are in all the engines that we use nowadays, outboard motors, car engines. We talked a little bit about electronic controls of power plant distribution areas and such. So I think that there's just a great deal of difference between these two areas. One area is kind of direct in like an electromagnetic pulse. You're just creating such a high EMI environment that the electronics don't work. And in the other area, you have high-powered electronic warfare, which is still using sort of the traditional methods of getting in a front door through an antenna or whatnot in order to do the work that it's trying to do. Now, within the field of high-powered microwave, you've had a traditional approach where folks have taken a TWT, so a traveling wave tube or some kind of a vacuum enabled device, a vacuum tube of some sort, and then pointed into a large parabolic that gives you a ton of focusing power around that microwave energy. And then that thin beam of energy is sent out as far as it can go. And it's not easy because you're putting a tremendous amount of EMI in the air, and the air is a big resistor. So the air is kind of really mitigating how far and how much you can push that energy through that air in order to have those same really profound effects. And so traditionally they've used TWTs and big parabolics to do the job. What Epirus does unique, and we believe we're unique kind of globally, we don't see anyone taking this approach yet, but we use gallium nitride solid state amplifiers, and we've architected it into a phased array. So instead of doing a TWT with a parabolic, we just have an active electronically scanned array that puts out not as much power as a TWT affixed to a parabolic, but puts out orders and orders of magnitude more energy. Because by using and leveraging solid state, we can create long pulses, because after all, as most of our listeners probably know, is energy is power integrated over time. So as we integrate our power over time, our energy is 40 or 50,000 times more than what can be delivered by a traditional HPM system. So within HPM, I would say if you double click down, you have two sort of variants. You have the variant that looks more like a phased array, a modern phased array, and then you have a variant that looks like an old traditional big satellite dish, a parabolic. And they have different ways and different methods they operate. With the parabolic, if I'll use this very simple analogy for the listeners, it's similar if the listeners have watched Star Trek. Star Trek has got photons that shoot out pew, and go long distances and maybe hit another torpedo coming in to hit it. And then it also has shields of energy that spread the energy around the ship, so that if 100 different missiles come at it, the shields are stopping all of those missiles. The traditional way of architecting HPM with a very thin beam, very short pulses, if you can imagine, looks kind of like a photon torpedo shooting out off of the Starship Enterprise to go hit 1 or 2 or 3 targets. Whereas the way that Epirus has structured the system as a phased array, it's much more like a shield. So we're able to very quickly scan the whole sky and put in the sky all of this electromagnetic energy at a big 60 degree by 60 degree wall, if you will, so that we can protect a base or protect a mobile convoy against any sort of incursions, no matter the quantity. Because what we've done is we've really focused on short range air defense in the lane of drone swarms. Many of these airborne autonomous systems flying together. And today, if you go after those with photons, meaning the laser beam photon, the high energy laser, or the old Thor type, you're only going to get a few at a time. And if you have 600 coming in, you're not going to get them all, or even with kinetics. And so what we provide is that last layer. So now answering the second part of your question, that last layer, that last final protective fires layer. In an airplane, you could think of it as like chaff that they shoot out of the plane at the last minute, kind of pulling out all stops. This is what our system does sort of similarly. We put out electromagnetic chaff that basically shields a base, but we can do that at a safe distance outside the fence line, but do it in such a way that we create these large areas, these huge volumes of electromagnetic energy that stand there and prevent hundreds or even thousands of these unmanned air vehicles getting through in order to penetrate a base.
That's really interesting, and you summed up a lot of the questions of what is this stuff and what is it used for. That's really helpful. So now I have a million technical questions.
Great.
So you talked about using electromagnetic energy to actually do damage to the electronics within these systems. Is there anything magical about the frequency that you're transmitting?
There is some magic about the frequency. There's magic about a whole set of different parameters around the actual waveform. So even though you're creating electromagnetic interference, the length of the pulse, the duty cycle, the frequency, all of these things are contributing to kind of the analog cyber effect that you end up having, or you end up being able to translate that to. So with the type of kill level, and they call that kill level, even though they just mean for electronics, not for people. But you have like a level 3, a level 4, or a level 5. And so a level 3 would be like disrupts the operation somehow. Like if you have a camera, it might make a bunch of fuzzy lines through it or whatever, and that's like a level 3. The camera's operating but not doing its job like it should. A level 4 is you disable the ability to use the electronics completely, but when the energy is removed, the beam is removed, you can start up the electronics again. Now that doesn't work well with drones because they fall down and smash into the ground. So that's what takes them out usually, is the ground fall when we do our effects. And then level 5 is the most damage. That's the laser effect. That's where the laser comes in and does total thermal damage to the circuits so that they're not usable again. You can't take a drone and start it up again once a laser takes it out. Or really, really high energy HPM. We operate at a really high power HPM. Really, really high power HPM. We operate at a lower power purposefully, and we target level 4. And so we do occasionally get 1 or 2 kind of capacitors that'll pop or something like that. But generally speaking, everything that we attack survives. But is completely and totally disabled. So the predominance of effects that we create across all frequencies, although the effectivity of each is actually determined by some of that answer to that question, we look at doing this at a level 4 level is what we've tuned our system to operate at.
You talked about using electromagnetic energy. Is there anything special about the frequency or other parameters in the energy you're transmitting?
Yes, sir. So there's 2 major things, I think, and you hit on them both. One is the thermal, and the other is, and the bigger problem for us, and I'll explain why in a second, our bigger problem is just what sometimes we say containing King Kong a little bit. And when we say King Kong, we're referring to the big, very powerful gallium nitride amplifiers that we leverage in our system. Those amplifiers, those gallium nitride amplifiers, are like King Kong, and you've got chains, which are the circuits and the elements around it that are the chains trying to keep control of King Kong. But as those power levels go up and up and up, and those power densities get greater and greater and greater, the electromagnetic interference that just pops right off of a board or messes around, or you get crosstalk, or you get point pieces of like corners and things that the EMI is so high, the localized EMI is so high, you can get plasmas, come out of the air and such. So you're really, really at that cusp of being able to push energy out so that it can get at some range and get through the air without creating lightning bolts and plasmas and things like that. So EMI becomes our largest challenge. And I'd say if Epirus has done anything really, really well over the last few years, is that we've learned how to contend very, very well. And we've got a lot of deep knowledge in our organization of how to deal with EMI on a high-powered system like this. The thermal question, we have less of issue with. If we continue to increase pulse width and duty cycle, we'll begin to have more of a thermal problem. But today we go at a very high peak power to average power ratio. Our average power of our systems only consume, let's say, 50 or 60 kilowatts whilst the machine is firing. But we're placing the duty cycle at such a low level that the peak power is quite high, is very, very high, but then it rests for a good amount of time. Not as long as a traditional system that might have a duty factor of 0.001 or even lower than that. And we've developed at Epirus a bunch of technologies, a family of technologies we call smart power, that are analog methods and analog circuits that basically help manage digitally the amplifier's nonlinear analog job that it does. So we look at output power, input power, we clean up the waveforms, make very clean, quick, fast rise times and fall times. And during the actual pulse itself, we do things to optimize at what level that gate is being biased and everything's being biased in order to give you maximum impulse efficiency. So our efficiency is so good at the system at this point in time that we don't even use any liquid cooling. We just have some big fans that blow some air through the system. We've run the system out at 110 degrees in the desert, in the atmospheric temperatures, 110 degrees. No issues, no real issues at all. So it's an elegant design that really kind of maximizes efficiency, maximizes conversion efficiency. And by doing that, we limit the amount of heat that we actually have to remove out of the system.
That's fantastic. And I think it looks like you actually have 3 different versions. You have a possibly looks like a portable, you have a fixed version, but you also have a UAV version, one that actually flies in UAV. Is it the same technology across all 3?
It is indeed, yes. We use the same supply chain, the same basic building block. We have a basic building block we call an LRAM, line replaceable amplifier module. And in the large system, that's purposely built for convoy protection and airfield protection, and those types of more fixed and semi-fixed applications. We're using the full-scale system, which is the largest of the systems, and that particular system has hundreds of LRAMs loaded inside. And then when you look down at the one you see being carried around on a drone, that one might have only 6 LRAMs in it. And therefore your range is much, much closer. And so the applications are different. So either the way you implement them, if you want to go drone on drone and then hover above something and fire that way, that's one application of how you can use the pod. But we've looked at other applications of the pod, and we've begun to study things like demining. These mines that are a few feet under the ground, they can be triggered by a very high electromagnetic interference. They can be triggered and detonate. So there's a concept out there where we could take a heavier lift drone, like by Honeywell has a hydrogen fuel cell type operated drone that can go for hours and hours and carry a pretty substantial amount of weight. In that case, you could take that over a field and look for mines by just radiating the ground with this ground penetrating frequency that we operate at. That is an application for the carrying a pod, for example. We've also looked at a lot of special operations missions, because again, it's not limited to drones. You can take out computers and switches and network switches and anything with consumer electronics are susceptible to this kind of an attack. And so on the electronic attack side, we have ideas about the pod for special forces as well. So a lot of really neat stuff as you get kind of to a mobile version of the system. And then the less kind of semi-mobile versions of the system, the large systems are for the much wider area kind of force fields or shields that you're trying to protect, larger area things like airfields or airports and bases and things like that.
Oh, good. I think on your website, you talk a lot about real-time machine intelligence to increase efficiency and maximize output. So what are some other, new technologies being leveraged to improve, HPM systems, things like AI, digital RF, intelligent power management system you've talked about. But what are some of the new kind of bleeding edge type advancements that you see in not just your product, but the entire field?
Yeah, that's a great question. And I'm gonna talk about kind of it under the context of AI, since you brought up the word, and I'm gonna use 2 examples of where we've integrated kind of very harmoniously AI into the advanced electronics work we do. First, I'll talk about at a low level. Since Pat's from Microwave Journal, we can talk at kind of the down in the weeds at the edge. Some people say it's at the edge or whatnot. Way down at the amplifier level, the 2 basic technologies that we utilize, and we use these differently depending on the use case, but I want to give you kind of a use case that's the whole kit and caboodle, if you will, the whole pie, would be using an advanced form of digital pre-distortion combined with an advanced form of high-powered envelope tracking, very high-powered envelope tracking. So on the front end, as the signals are coming into the nonlinear amplifier, we're using digital pre-distortion, but not kind of yesteryear's digital pre-distortion. We're taking basically a look at everything coming out of the amplifier, and real time, we have a small little neuronet inside of an FPGA, just, I forget, a couple nodes, not anything too fancy, but it amounts to being kind of a control loop where we're sensing what's going on in the output of the amplifier and what's it actually looking like. And then going back to the front end and saying, how can we, in real time, not on a lab bench, inside the circuit, change the way we pre-distorted in order to come in a different way? And by doing that and slewing and also modulating the gate, we can actually kind of achieve per amplifier optimal performance. So each and every one of the amps gets its own kind of constant sort of oversight, making sure that any performance variations like nonlinearities and stuff like that can be taken out by the pre-distortion of the signal coming in. And then the second thing we do, and a lot of times envelope tracking, I like to think of as you're taking in a small RF signal to make a big RF signal, you have a great big water main, the big pipe coming in, and we usually call that the drain. If we have a common source configuration that's coming down the drain and flowing into the source, that big pipe is normally left in circuit design wide open. There's no valve there. It just is wide open, and when the transistor needs energy, it pulls it. When it doesn't need energy, it doesn't. So when it doesn't need as much energy, there's some leakage in through that amplifier, and it can be significant. So what we do in our high-powered envelope tracking is we modulate that DC drain voltage, and we make sure that when the circuit doesn't need excessive drain voltage and a drain supply, that we go much down on, dial way down on the voltage. And then when it needs a full blast voltage, we dial way up, almost like having a valve on the input of the actual amplifier. So we do those two things really, really well. And in an example of that, we're working very closely in partnership with L3 Harris and on the Harris side of the business in Rochester in order to clean up that transmit chain in the way that I just stated. And by doing that sort of a thing, you get way better efficiencies that allow you to have advanced waveforms that have all these different modulations that might overheat or not work on a traditional transmit chain. These now do work. So not only do you make a cooler device, a higher powered device, a longer battery lasting device, these are all the benefits you get. You also can do signals in some of these radios that you couldn't even support, but now that you've gotten the efficiency up to where you need it, you can actually run a whole bunch of new signals on these older sort of tactical radios. So that's the tactical radio. The converse, of course, is EW. We do a much lesser amount of that inside of Leonidas's transmit chain because it's a much more basic chain today than such a tactical radio or advanced EW system. So we do both. We have a group called Advanced Electronics that we embed sort of this tech into folks, and then we also have a bit of it in our system level. So that's at the circuit level. Now, at the highest level of the system needs to be able to spot, track, find these drones. And then once they find these drones, it needs to be able to have some amount of intelligence around what is this drone, whether it is a Phantom 4, it's a Mavic, it's a this, it's a that, exactly what it is. Or in a class of vehicles, it's sort of like this type of vehicle, a quadcopter, a fixed wing, so on and so on. So you're needing to even identify. And the reason why I say that is in order to kind of tune our system to the best possible effects, we need to understand what it is we're kind of going after. And there's some very special secret sauce in there that kind of helps with becoming more lethal and more higher, much more longer range and much more higher probability of kill by getting all the waveforms right. So when you look at the short range air picture and you consider drone swarms, you begin to say, the way that 50 years of air domain superiority of doing kind of a long range radar, a more higher frequency targeting radar, maybe an EO system, an IR system to track, and then we shoot a missile out after it. That staged approach to kind of handoffs doesn't work on drone swarms, doesn't work on the short range air picture. We're talking maybe out to 10 kilometers. Maybe up to 1,000 feet. And we're not talking just like Tower 22 in the middle of the desert. We're talking inside of jungles and forests and cities. It's a very, very dense environment. Now you couple to that very dense environment hundreds and hundreds of drones popping up everywhere, coming from every which direction, blending into the buildings, blending into the background, blending into the trees, blending in or confusing with a bird. It's almost an impossible mission for the traditional way of defending the long range air picture, the traditional way. So what we've done at Epirus is we've got an effort underway where we're taking the best and brightest out of autonomous driving. So looking at the way Tesla consumes a scene, right? When you look at 500 yards out of a Tesla car, it's taking everything in a singular gulp. 5 or 10 times a second, it sees 360 degrees around itself and identifies everything. If it were to do it in a serial manner, it would never keep up. You have too many things going on. So this is the advantage of the modern AI engines, these NVIDIA kind of, why NVIDIA is so much money nowadays, the guys getting all the press, is because they are so good at doing kind of AI jobs. And at a high level, at a system levels, that's what we need. We need a system or an architecture of a system that uses big data and the ability to look out 5 kilometers up to 1,000 feet and identify every single thing in it 5 or 10 times a second and keep that rate up. That's what's needed. So AI is paramount to winning the short-range air dominance battle. So to regain or to recapture air dominance over what we've been seeing lately, we need to know everything inside that pie that I've been describing. And in order to know everything inside of that pie and what's going on, the only technology that we see that's able to do such a job is big data and AI. And so that's what our Seattle office specializes in. And what we're doing at a high level, at a system of systems level, to partner with the low-level AI stuff we do kind of embedded in our actual circuits.
GaN technology is probably one of your limiting factors. What needs to improve in the coming years on the technology front to continue advancing your systems to the next level?
Well, I guess it's a couple things, and it is centered. You're right into kind of lead me a tip of gallium nitride. It's kind of centered around gallium nitride, but there's it quickly branches out into a couple of different areas. Obviously, we leverage the highest peak power we can get, out there in the industry, and therefore that usually is driven by very, very high breakdown voltages, higher and higher breakdown voltages, and then affiliated with that, the associated bias level. So if I can get to 100 volts bias, then I can get to maybe a 7,000 watt gallium nitride part, which is what MACOM has right now. Actually, they showed it at an IMS show about a year ago. They have a 7,000 watt, I think 100 and some odd volt biased gallium nitride part. And so that is really dealing at a small little discrete level with some of these big EMI challenges that we deal with at a system level. They're having to deal with kind of at the micro electronics level. And so that 7,000 watts is great. That we want more power. The more power we can get in a device, the better just in general we have to go do all of our magic with. It just gives us much more clay to work with. But then, of course, as you get into those higher peak powers and then even higher, longer duty cycles, longer pulse widths, you end up getting more and more into the thermal problem. Because just as even if you're at 70% of 7,000, you still have thousands of watts of heat. If I'm converting, let's say I'm converting at 50% efficiency, I have 3,500 watts of heat to get out of that small little chip. it's not an easy thing. It's not, I've been working on this since I was at NGJ, a guy, and figuring out how do we get all of this heat out of this tiny little gallium nitride device. And think of like 60-watt bulb. Think of how hot that is, or 100-watt light bulb, an old incandescent light bulb. Figure out how hot that is. Imagine getting out a couple thousand watts of heat under every single one of those transistors. So there's a lot of really advanced thermal work being done. But when you look at where the market's going, they're going to things like phase change material in order to have that extra energy kind of without changing temperature so much, able to absorb a lot of heat energy through phase change material. They're looking at submersion, full submersive systems that are completely under water, metaphorically speaking, And if you look at things like the power conversion in data centers and stuff, they're looking at fully submersed, power conversion shelves and stuff like that, and fully submersed even compute in order to get rid of that heat in a submerged tank of some sort. So we're looking at better and better ways of dealing with thermal heat, and then of course EMI. So it really comes down to advancement in GaN, I think, in those two vectors, the same vectors we talked about that we contend with at a system level. Now, beyond that, what we kind of specialize in is holding the chains around those big King Kong gorilla gallium nitride. And we've looked at things like, this is way down in the weeds for maybe some listeners, but, getting a PCB board that actually can have a top layer, that gives you some amount of RF protection. So you don't just have the single layer board just radiating out into the air. You can kind of encapsulate those traces inside and make much more square traces, much more physically square traces that have much better electrical conductive property than when you kind of get the sort of the hump over the top of a trace when you just have an open air board. So things in that nature we've been looking at as far as EMI and figuring out how new architectures that we can really chain in the gallium nitride. So if I had to say three, it would be higher voltage gallium nitride, better EMI type stuff and resistance, better thermal. Obviously, as we get higher and higher power, we need better and better thermal solutions. And three, just the circuits and the boards around such high power, ensuring that the circulators are ready to go, that other parts and pieces and switches, combiners, things like that also can deal with the same increase we're seeing happen year on year on gallium nitride. As that rises, things need to rise with it in order to actually build something with it versus just having a huge demonstrative amplifier that doesn't work with anything else.
We've talked about UAVs, we've talked about IEDs, even mines. What other applications would you see this technology could have evolved into?
Yeah, it seems to me that everything we've tried, we even had a program we called Will It Zap, for a while. Every single thing that is made in the consumer electronics space is highly susceptible to being disabled by this kind of technology. So you can think of night vision goggles as a potential target, computers, computer switches, vehicles, cars. They're all run by computers these days. And the more Tesla computers you put into the car, the more susceptible they are to this type of an attack. So we've done studies on cars built before 2015, after 2015, and we see big differences in the susceptibility to these types of attacks. It could be used against outboard boat motors that we've demonstrated, and we plan to demonstrate this year with the Navy in an exercise coming up in June called ANTX, ANTX, that they've been doing for about 8 years, where we're going to show effectivity of a scaled size system that you could imagine mounting maybe on the front of a rib boat and just having a rib boat out there patrolling the Red Sea. And if you see a USV coming in or a hostile actor in one of those commercial lanes, being able to zap that outboard boat motor and shut her down so it doesn't have any ability to operate until you decide to let them go. So I think there's a ton of different applications. I'm in LA. That's where we're based out of LA. Every other night we see a guy running down the highway, escaping all these police. If you put one of our systems on the front, no more car chases. I guess that would be a entertainment hit for us. But there would be no more car chases. The guy would get in his car, you'd turn on the front end of one of these systems mounted on a hood, and it would shut down the car engine. And then the guy would have to just step out and get caught. So a ton of different application. I think we're at a tip of an iceberg of a new class of sort of electronic warfare, a new type of electronic warfare that has, I think, almost unknown applications at this point since it's such early days.
What are some of the challenges that are keeping companies from fielding and operating the system today? So can you tell us, like, are you still in your prototype stage or beyond that?
Sure. Yeah. And I use the word prototype. I'm talking operational prototypes that the military uses operationally. So these are not, in a lot of people's minds, you can think of them as early production ready. We have in Torrance, California, where we're headquartered, 100,000 square feet. Most of that is manufacturing space. 60 or 70,000 is manufacturing space, where we're able to build on if we just baseline on the large system, we can build about 4 of those per month, leveraging 2 shifts. So we can get 48 systems a year out. We've built to date for delivery to the customer 4 systems. We shipped all 4 of those systems as of March, and in April, actually, we have a very big event, a limitations and capabilities event. 2 of those systems we sold to the Army and do a bunch of limitations and capabilities type testing. So that's what's in store for us in April. And then beyond that, we have the next phase of what we're going to get into as a company is we get into going out and operationalizing these guys. So going out to the CENTCOM, going out to PACOM, potentially Ukraine. All of that has been introduced as on the table, pending successful results out of April. All of those things are on track. We're currently under contract under what's called an MTA, a mid-tier acquisition route, where you usually use something called OTAs, these contract vehicles, in order to rapidly advance. And how Dr. LaPlante defines the MTA is a 3 to 5 year development to fielding cycle that can cut into a FAR program at milestone C or can go straight to delivery. I mean, we have the optionality to go from where we're at today, iterate, and go straight to production. If we do that, it's likely we'll be in a full rate or at least a low rate production come about 2026. If we end up cutting in a little earlier in the development cycle, you may see a lot of prototypes getting news and press out there, but the production systems will be likely 2027. That's sort of how it all spaces out. Now, that's what our customer has given us, right? That's what I've given. Not to say we're not ready to go faster. So if the government needs us to go faster, we stand by ready. We stand by to go at a year pace, 6-month pace, 2-year pace, whatever it is. But now we're about 18 months into a 3 to 5 year MTA type acquisition path.
So I guess I'll close out one last question. We've talked about applications. What does this technology drive over the next maybe 5 to 10 years? And I guess the question that I'm really curious about is, will there actually be now a counter system to that starts protecting the drones or starts, for example, protecting cars, right? If that becomes a vulnerability, is that going to drive, the Teslas of the world or some of the other automotive companies to have to be able to protect against that? Or maybe my, 1969 442 suddenly becomes bulletproof, which might be good. So I'll let you close with that question right there. So
I'm gonna close on this question, but I'm gonna talk first a little bit about what's going on a global level that's driving kind of a need for this type of a thing, and it's paramount to basically a deterrent, because if you look at the state of affairs today, we cannot confidently claim that we have air domain superiority. I mean, Tower 22, I know it's one incident, but we lost life. And I think a lot of critics are saying, how can we possibly claim when we have one drone that comes in and does that kind of damage? How can we claim today that we have air domain superiority in that close range air picture? And our potential enemies know this. China knows this. Russia knows this. And they're gearing up to be able to build an enormous amount of four-man cruise missiles is what they turn out to be. It's let's build 100,000 of these a month or 200,000 of these a month. This is the numbers that they're talking about. And then what we'll do is we'll flood the skies with thousands and thousands of these. The US will respond by launching Patriot missiles and Stingers and other kinetics, and we'll deplete their arsenal with them. We'll take toys and deplete the arsenal, the military arsenal of the US. And then therefore, we'll just send our missiles on in. They won't have anything left. This is what's in the mind of China. This is what's in the mind of Russia, that they can win the fight through attrition and trading out the more sophisticated systems by these poor man's cruise missiles. And you see that playing out in the Red Sea today. You see that going on with today. They're sending in sea skimmers, poor junky cruise missiles or drones that come in and do tons of damage. And we're just sitting there watching them. Task Force 59 is like, what do we do? Now, enter Leonidas, enter these shields that I'm talking about. Now, think about the deterrent. If we line up along the coast of Taiwan, a bunch of Leonidases that the Chinese know that no matter if they send 1 million drones across the Taiwan Straits and they all get kerplunked into the water. So they're wasting their time building an arsenal of toys that we have an effective machine to counter. So the deterrent to a large global war, I think, can't be overstated. That this is a psychological thing that we got to say, look, we can't meet your volume manufacturing of consumer electronics in the US ever. Like that won't happen. China will be able to outpace us in building small drones. They just will. Therefore, we have to counter them with technology, which is what we've always done in a superior manner, especially when we talk about high-powered advanced electronics like what we do at Epirus. And so by pairing those two things together, you've reestablished air domain superiority. And you no longer have these kind of sneak pads that they can get by you by flooding the air with drones or sneaking them in some way like they did in Tower 22. So that's one that I wanted to say. So because of that importance of this mission is so dramatically important, of course we have to think about the cat and mouse. Of course we have to think about now that we've done this, they're going to shield their cables more. They're going to put stuff in here or there and try to make the system more robust against electromagnetic interference, like an airplane. An airplane's very robust against electromagnetic interference because you get solar storms and things way up at high altitudes that can affect electronics. So they have to be robust against electromagnetic interference. The problem or the difference between a large jet and a small drone is weight capacity. These guys can't carry hardly anything. I mean, they're ripping the lids off the things that have the exposed electronics just to save on weight. And so they have a real weight swap problem that it's hard for them to actually add a lot to the actual structures and still get them to run or fly. Now, not the same is true with cars. They could add robust ways of creating more and more electromagnetic interference protection. But the way our system works in the smart way, and the software-defined way, very much like my old brother, Next Generation Jammer that I used to run and manage, is that it has what's called a software-defined back end. And through having that software definability, as the problem childs out there create new robust ways of protecting, we can just through software adapt to those protections. So a Faraday cage has a very interesting quality about it. If you penetrate a Faraday cage, you immediately lose 90% of the goodness of it. And in fact, it can actually work against you. We find that if you have penetration to a Faraday and you can figure out how to get the wave into the actual Faraday cage, it tends to stay in there. The energy doesn't radiate then out again. So it ends up bouncing around in there and causing even more damage. So there is definitely to be played out a cat and mouse, but we've thought about those steps already at Epirus, and we've put in the right hooks and the right system architecture in order to already take 2 or 3 more steps towards the future. And so I think combined with the gallium nitride advances that we talked about, plus the software definability, plus the advanced weaponeering and the different research we're doing in order to see really how these effects work, we have a very, very robust system that is, I think, paramount and so important in order to deter this war of attrition that's beginning to be talked about and played out. And we have other programs like Replicator and others that are out there trying to contend with it. But this is the way Epirus is offering to contend with it.
No, that sounds great. Thank you, Andy. And I'll turn it over to Pat to take us home here.
Thanks, Sean and Andy, for your insights related to drones and other autonomous vehicles. If our listeners would like to recommend any topics or have any comments on this podcast, please email me at phindle@mwjournal.com. Thanks for listening.